So hello all, in this video we will continue to analyze the oracle complexity of the subgradient descent. We will consider the non-smooth strongly convex case now. So in the strongly convex case, the result is that for mu strongly convex function f, which is also LF Lipschitz continuous, in order to ensure that the best optimality gap is less than epsilon, the required oracle complexity is given by order of LF square by mu epsilon. For the step size, eta t equal to 2 by mu times small t plus 1. The interesting thing to notice here is that the rate is much worse than the linear convergence rate we have obtained for PGD, but the proof will be somewhat similar to that of the Frank-Wolfe algorithm for convex case. So the proof starts in the same way. Using the non-expansiveness of the projection operator, we have that norm square of xt plus 1 minus x star less than equal to norm square of xt minus x star minus 2 eta t inner product of xt minus x star comma gt plus eta t square norm square of gt. Now here, instead of using the first order condition for convexity, we use its generalization, which is the quadratic lower bound on the second term, so that we obtain norm square of xt plus 1 minus x star less than equal to 1 minus mu eta t norm square of xt minus x star minus 2 eta t f of xt minus f of x star plus eta t square norm square of gt square. So this is our one step inequality, and this we will keep it for now and carry it over. So to solve this recursion and to solve the oracle complexity, we will use the same technique that we learned in the context of Frank-Wolfe algorithms. First, substituting eta t equal to 2 over mu times t plus 1, we obtain norm square of xt plus 1 minus x star less than equal to t minus 1 by t plus 1 norm square of xt minus x star minus 4 over mu times t plus 1 f of xt minus f of x star plus 4 LF square by mu square t plus 1 square. Next, as before, we can multiply both sides by mu times t plus 1 so as to obtain that mu t plus 1 norm square of xt plus 1 minus x star is less than equal to mu t minus 1 xt minus x star norm square minus 4t f of xt minus f of x star plus 4 LF square by mu into t by t plus 1. So this allows us to write the telescopic sum and obtain that mu t times t plus 1 into xt plus 1 minus x star norm square is less than equal to minus 4 summation over t equal to 1 to capital T minus 1 small t times f of xt minus f of x star plus 4 LF square by mu summation over t equal to 1 to capital T minus 1 t by t plus 1, where the x1 dependent terms goes away because t equal to 1, eta 1 is equal to 1. This is the final inequality that we would now need to simplify. So let us carry it over. Observe that the term on the left is greater than or equal to 0, and the first term on the right can be bounded by the minimum optimality gap definition, and each summand in the last term can be upper bounded by 1, so that we obtain that 0 is less than or equal to minus 4 f best of t minus f of x star summation of t plus 4 LF square t by mu. So rearranging this, we obtain that f best of t minus f of x star is less than or equal to LF square into t divided by mu times summation of small t, which will give us 2 LF square by mu times t minus 1. So equating this to epsilon, we see that the oracle complexity is the required order of LF square by mu epsilon. So a point to note here is that we had dropped the first term on the right. Instead, we would have obtained that norm square of xt plus 1 minus x star is less than or equal to 4 LF square by mu square into t minus 1, which again yields the similar oracle complexity, just using a different distance square metric. So with this we are done with the analysis of the subgradient algorithm. We have seen that because of lack of smoothness, the oracle complexity was higher than projected gradient descent. But the fact that we do not require smoothness also makes the subgradient algorithm highly flexible and very broadly applicable in general. Before concluding, let us look at an example application of subgradient algorithm on the problem of projecting onto the intersection of sets of x1 and x2. Assume first that the projection on either x1 or on x2 is easy. So it turns out that despite the fact it may not necessarily be the case that there is an efficient algorithm to project onto the intersection of x1 and x2. The same is true when we are projecting onto multiple sets. So even though it may be easy to project onto each of them, the projection onto the intersection may not necessarily be easy and may not admit a straightforward closed form solution. So to solve this problem, let us consider the minimization of the objective function. So minimize f of x, where f of x is equal to the maximum distance of x from x1 and the distance of x from x2. We recall that the distance of x from calligraphic x is nothing but the norm of x minus px of x. If the intersection of these two sets is non-empty, then f of x star will be equal to 0. So this is the maximum of the two functions. So it is a non-smooth function. We have already shown that the subgradient of the distance function is given by x minus px of x divided by distance of x comma calligraphic x. The subgradient of the max of the distance function is basically the subgradient of the distance function for the index that maximizes that distance. That is, for any point xt, gt equal to subgradient of distance of xt from xi, where I is the index that maximizes the distance of xt from calligraphic x. In other words, for a given xt, we are finding the set that is farthest from it and then calculating gt using the formula of the subgradient of distance function. So the subgradient algorithm in this case gives rise to another well-known classical algorithm called the alternating projection method. To see this, the subgradient updates are given by xt plus 1 equal to xt minus eta t gt. In this case, f of x star is equal to 0 and f of xt equal to distance of xt from calligraphic xi, where I is the index of the set that is farthest from xt. Since we know the optimality gap, we can use the Polyak's step size rule. Therefore, the update is given by xt minus distance of xt divided by norm square of gt times xt minus pxi of xt divided by distance of xt from calligraphic xi. Note that here norm square of gt is 1, so things cancel out and we will get the algorithm xt plus 1 equal to projection onto calligraphic xi of xt, where I is simply mod of t comma 2. So the reason for this is that once you project onto x1, automatically x2 becomes the farthest set, and then if you project to x2, x1 again becomes the farthest set. So this is the alternating projection algorithm. The algorithm entails alternatingly projecting between sets x1 and x2 in order to find their intersection. From our analysis, we can see that after t iterations, the distance should decay as order 1 over square root t, which is actually the rate we derived for subgradient descent, but is actually known to be the optimal rate for the general alternating projection method. The figure shows the alternating projection method in action. As you can see, there is a lot of zigzagging going on. You can verify that if you used a constant step size, the size of these steps would not have dropped with t and you would have seen oscillations throughout. If we plot the distance as a function of iterations, we would see that it is not going down linearly. Now suppose that we consider the same objective but the sets x1 and x2 do not intersect. If we apply the alternating projections method, we would see that the iterates keep on jumping between calligraphic x1 and calligraphic x2. However, if you look closely at the objective function, you would see that it is minimized at the point that is midway between x1 and x2. The alternating projection algorithm is, however, not giving us that midpoint. So why is that? The reason is that we use the Polyak step size, which required us to substitute f of x star equal to 0. However, in this case, f of x star is actually non-zero and in fact unknown. So the Polyak step size with f of x star equal to 0 is not a correct one. And that resulted in alternating minimization algorithm, which would also not be correct for this problem. So in this case, we have the non-intersecting sets and we have the general form of the updates given by xt plus 1 equal to xt minus eta t times xt minus pxi of xt divided by distance of xt from calligraphic xi. So as before, we have that I is equal to mod of t comma 2. Since f of x star is non-zero and in fact unknown, we cannot use the Polyak step size. So we use the usual eta t equal to 1 over square root t. So as you can see in this figure, when using a diminishing step size, the iterates will not go all the way up to the sets but stop midway only. This is also a zigzag behavior, but the amplitude is less and is typical of the diminishing step size subgradient method. And you will be able to see this in many problems. Let us consider an interesting example that demonstrates a link between Frank-Wolfe and projected subgradient methods. Consider the projection problem that px of u is given by argmin of x in calligraphic x, half of x minus u norm square. Suppose that the projection onto calligraphic x is not available readily in closed form or via bisection. So one way to calculate the projection iteratively is using the Frank-Wolfe algorithm, which would take the iterations yt equal to argmin of y in calligraphic x, x minus u, comma y. xt plus 1 equal to 1 minus eta t xt plus eta t yt. Note that this is not for use in the projected gradient algorithm. This is just to calculate the projection one time because the rate here would be much slower. Let us look at another way to calculate the projection. First, we can write the problem as px of u equal to argmin over x in v and y in calligraphic x minus inner product of u comma y plus half of norm square of x, where we have dropped the sum of the constant terms such that x equal to y. So here we have freed up x to take arbitrary values in v while constrained y to be in calligraphic x. Then associate Lagrange multiplier lambda with the constraint so that the Lagrangian is given by L of x comma y comma lambda equal to minus u comma y plus half norm square of x minus inner product of lambda comma x plus inner product of lambda comma y, which can be written as inner product of lambda minus u with y plus half x minus lambda square minus half lambda square. So let us keep it for now. When we minimize L over x and y, observe that minimization over x becomes very easy because x is in the full domain V. So the optimal value is simply x equal to lambda. Therefore the dual function is given by minus half norm square of lambda plus min over y in calligraphic x inner product of lambda minus u comma y. Now suppose that we want to use the subgradient method on this dual. Since the dual function is concave, we would consider the iterations lambda t plus 1 equal to lambda t minus eta t gt, where gt is a subgradient of minus rho of lambda t. To calculate the subgradient of the negative dual function, we can recall the envelope theorem, which states that gt equal to lambda t minus y of lambda t, where y of lambda t is argmin over y in calligraphic x, inner product of lambda minus u, comma y. So the lambda update becomes lambda t plus 1 equal to lambda t minus eta t times lambda t minus y of lambda t, or equivalently lambda t plus 1 equal to 1 minus eta t into y lambda t plus eta t into y of lambda t. This is identical to the Frank-Wolfe updates in the primal domain. So this is one interesting connection or some sort of duality between Frank-Wolfe and subgradient algorithms that was actually not known earlier, and it was only recently established in the last decade. There is a generalized version of the result that is also available. Note further that the complexities are also same. The complexity of solving convex projection problem using Frank-Wolfe is order 1 over epsilon. The dual function is strongly concave, so the complexity of solving the strongly convex dual problem via subgradient descent is also order 1 over epsilon. So let us summarize the results that we have seen so far, and that for that purpose we will compare the oracle complexities of all the algorithms that we have seen so far. We will write down the convexity related assumptions, then we will write down the oracle complexities for projected gradient descent, and then for Frank-Wolfe method, and then finally for projected subgradient method. The complexities for projected gradient descent and Frank-Wolfe will be for smooth functions only, while those for projected subgradient will be for general functions. So we begin with looking at the general case where both projected gradient descent and Frank-Wolfe achieve complexity of order 1 over epsilon square, while the projected subgradient method is not applicable in this case. Next, in the convex case, both projected gradient descent and Frank-Wolfe method achieve the complexity of order 1 over epsilon, while projected subgradient method achieves the complexity of order 1 over epsilon square, which is at par with the general smooth case. Finally, for strongly convex case, projected gradient descent achieves linear convergence, order of log 1 over epsilon, while both Frank-Wolfe and projected subgradient method achieve order 1 over epsilon complexity. We didn't have any specific result for strongly convex case in Frank-Wolfe, so the result from convex case carries over. So in summary, the projected subgradient descent is much worse, primarily because of the lack of smoothness inherent to the problem. So that is all for this video. We are done with our analysis of the subgradient method, and we will start with the mirror descent in the next video.